So how does this turn into side channel attacks? Well, so I'm just taking a general definition here of side channel attacks. We're going to talk here about specific microarchitectural ones, but really, a side channel is any way that you can monitor a device and infer something about its operation. So, a classic one is if you have a bank card with a chip on it, one thing that people like to do is differential power analysis on that chip. So you put it into a reader, and then you monitor the power pins. And you see, OK, while it's doing this operation, here's the current fluctuation. And you can monitor that, and you can infer something about the operation of that chip. And so the banking industry has invested large amounts of money in building tamper-resistant designs and in removing the ability for you to do this differential power analysis. But the point is there are lots of different side channel attacks, and they will continue to exist and continue to be found. So caches as side channels. Well, computer caches exist because we're trying to speed up accesses to memory, right? We have small amounts of memory on our processor. They're storing recently used data, and so the presence of a value in the cache will alter the access time to access a particular memory value, right? If it's in the cache, it will be faster to access it than if it's not in the cache. So what I can do is I can use a high-precision timer. I can measure the current time, perform an access, measure the time again, and compare it to a calibration to work out what's that data present in the cache. How does that relate to these vulnerabilities? Well, let's go through them one at a time. Let's do Meltdown first. So Meltdown is about speculation about permission to access memory. So here's an example of a branch, right? I'm going to perform an access to some memory location. I'm going to try to access a pointer to which I shouldn't have access. And then I'm going to do something based on that pointer. And what should happen is, the moment I try to access this memory address, because, for example, it's a kernel memory address, something I don't have access to, what should happen is immediately, that should not happen. I should get some kind of exception. I should get an error condition. My program should terminate. But what actually happens in Meltdown vulnerable designs is that we continue to speculate ahead, and we catch this exception later. We handle it a little bit later than just killing it immediately. So I try to read something from memory that I shouldn't have access to, and I perform a second access based on the value that I read. And that second access is going to pull something into the cache that I can then measure later. So I'm not actually, I'll go through what happens underneath. So what happens underneath? I perform an access. The process is going to say, at some point, I should flag this because this is an illegal memory access. It should kill it before I perform a second access, but it doesn't. And so a really bad thing happens because I'm able to perform some second memory access based on the first. And the second memory access is going to pull something into the cache. That's going to alter the timing. When I later go and walk through memory, I can work out, is this value cached or not? And based on whether that second value is cached, I can work out the content of the first. All right? So Meltdown requires several conditions. You have to have privileged memory mappings at the same time. You have to have kernel mappings in place at the same time that you have application mappings, which is traditionally the case in modern operating systems. And in some cases, the data must also be in the innermost L1 cache. So what we can do, since we can't go and change every design that's in the field, what we do instead is we, for example, separate our page table mappings. We separate it so that we now have a separate view of memory when we're running operating system code. This impacts performance, but it means that when I'm running in my application state, there's no valid translation. So if the processor tries to speculate ahead and perform an access, it won't succeed. In other cases, I might just say, well, I'm going to flush the cache whenever I return from performing a privileged operation. That's slower, but in some cases I might do that instead. Keep going. All right.
No,
Yeah.
stay.
Oh, stay here.
Yeah.
Okay. Okay, so let's talk about Spectre. So Spectre is about exploiting what are called speculative gadgets. Right? So a gadget is a piece of an existing program that I'm going to exploit. It's not something that I write. It's an existing program, existing code, but I'm going to abuse it. And a classic example of gadgets is something called return-oriented programming, where an attacker would kind of string together pieces of code and perform stack-based buffer overflows and kind of exploit existing code to do something nefarious. We can do something similar with speculation. So in Spectre v1, what I do is I have a branch condition. I have a, is this data that I'm reading, is it within bounds, right? I have some data I'm going to process. I do a check to see is the offset that I was given by some untrusted user, is this within bounds of, for example, an array containing some data that I want to read? And the processor might decide to speculate ahead. It might decide to guess that this access is going to be within bounds. So following that prediction, I can do a similar second, I can load a value, perform a second access, and again, I can use cache timing analysis to infer the content of the first value. So existing hardware lacks the ability to limit speculation in this case. And mitigating what we call Spectre variant 1 is actually a huge problem. So today we've really got two ways we do it. We can define or add special instructions to serialize execution to say, basically, don't speculate after this point. Right? That's expensive, but we can do that. The other thing we can do is we can speculatively clamp the access. So what do I mean by that? I mean that we can write some very clever code that will allow speculation to happen, but it will mean that when we do speculate, we're always speculating within bounds of that array. And so what we've done in the case of Linux and other operating systems is we've written analyzers that will go through potentially vulnerable code, for example, the kernel, Linux kernel, and it will look for these kinds of out-of-bounds access that we might perform based on some untrusted offset. And then we've had to go through manually and add these different checks. Right? This is an expensive mitigation, requires actual code changes. Second part of Spectre affects indirect branch prediction. So as I said, when we're calling a function through a function pointer, a virtual reference to a virtual method or a reference to another function, we might try to guess where that call is going to go. And if we don't use enough bits in the address to disambiguate between two different possible indirect pointers, we could effectively alias them to the same location in our predictor. And so we can do something called predictor poisoning, where we can write some malicious code that's going to train our branch predictor to guess that next time we call this function, we're going to go here. Actually, it should go there, but because we write some code that's going to repeatedly make calls that look like it should go here instead, we're going to mispredict it the next time. And so how do we address Spectre variant 2? We address Spectre variant 2 by effectively flushing branch predictor state. Right? We can change the hardware to make the branch predictor not have this problem, but that obviously requires physical hardware replacement and so on. So instead what we do is we add the ability in our software to flush the branch predictor state or to limit speculation based on branch predictor entries. So there's a couple of different approaches. There's a big hammer approach, and we've got various instructions that we've added. For example, on x86, IBRS, indirect branch restrict speculation, that says, I'm about to go into the operating system. I would like to restrict speculation based on indirect branches. It's going to hurt performance, but you're not going to hit this condition. And then we have a barrier we've added, indirect branch predictor barrier, that will flush the branch predictor state. There's another trick we can use, ret pollines, that Google invented, which basically say, we're not going to disable or impact the behavior of the branch predictor, but instead, we're going to cause harmless speculation. So you might want to look at this code later. It's kind of a complex concept. But basically what we do is we say, I'm going to call a function. I'm going to intentionally, you see the capture spec line there, I'm going to intentionally set things up so that if any speculation occurs, it speculates into an infinite loop, right? A harmless infinite loop. And there's a little trick here we do with changing our function return stack to make the function call. And so with retpolines, we have to modify our software. And we've done that for the operating system code out there, for example. But we don't have to disable branch prediction. I'm going to keep going. And there are various complexities here. As I said, sometimes we have return stack prediction. That can really interfere with some of our mitigations as well.